In this video, we're going to talk about modeling data. Our objective: determine an appropriate function for modeling data in a scatter plot. Okay, let's first review what we know that we're going to use in this video. We know what a function is, an equation in two variables that relates an input to an output. Functions can be written using the y equals notation or f of x equals notation. And of course, when we have a function, two variables, then that sets us up for number 2 here, a scatter plot. A scatter plot is a graph of plotted points. Well, with a function, we have two variables, an input, the x value, and an output, the y value. Well, that can be graphed in a scatter plot. The plotted points that show the relationship, if there is one, between two sets of data. So these two things go together. The function, of course, is the equation side, and the scatter plot or the graph is the graph side. Okay, we have seen and talked about linear functions or modeling data that's linear. Some data can be modeled using a line, and that's what we would call a linear function. Again, that root word line right here. I can underline it for you. However, the data is not always in a line. Okay, if the data are not linear, there may be a different function that can model it and then can be used to make predictions. The other ones that are most popular, the other functions that are used to model data, they include an exponential function, a logarithmic function, and a quadratic function, which you may or may not have heard of. If you had, obviously that'll help you a touch here, but I'll go over these. So let's take a look at these plus the linear function with some examples. I'll come down here. And first, what I have here for my table is what the data points in the scatter plot will look like. An example, which we'll put a picture of over here, and then the name of the model or the name of the function that best fits the data. And so here's our linear example. We have data that looks like it's kind of a straight line or nearly a straight line. A good example for this is your height versus your weight. And a linear function will model that. Let's take a look with a simple graph. Okay, nothing fancy. I'm going to do first quadrant, kind of real life stuff. And so the x-axis is your height. The y-axis is someone's weight, height or weight. And generally speaking, as our heights, and I'll put some dots in here, as our heights get long, I guess as we get taller, as our heights grow, our weight increases. Okay? So, it makes sense if you think about it. As we get taller, people get heavier. And you can somewhat, there's not going to be a perfect linear, but you'll get a sense that this data tends to be modeled with a straight line, or can be modeled with a straight line. Okay, height versus weight. In general, it will kind of grow kind of consistently. Taller people, way more. Shorter people, way less in general. So there's an example that we're aware of with height and weight. Let's take a look now at an example for exponential. Let me turn my paper over. Okay, so here's an example of exponential growth. And again, what does the data look like? Well, it increases or decreases more and more rapidly. Okay, exponential growth, whoop, goes up quicker and quicker and quicker, or goes down quicker and quicker and quicker. But normally we see it kind of going up, exponential growth. A good example of this are number of cells, human cells after conception. Of course, we start with the sperm and the egg coming together, and then that splits, and then they split, and then they split, and then they split. And the number of cells grows very, very quickly. It grows exponentially. Okay, that's our model here. So again, let's make it just a simple first quadrant graph. And we'll label the x-axis time, and the y-axis is the number of cells. And again, at time 0, we might have 1, but the number of cells, as they split and split and split and split, and they each split, it grows faster and faster and faster until it reaches something like, I don't know, 3 trillion or something human cells. And so here's the model. Here's exponential growth right here, okay? So as time goes forward, the number of cells that make up your human body increase faster and faster and faster. As they subdivide, 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 each of them, they get quicker and quicker. It gets faster and quicker. Okay, so there's an exponential example of exponential growth. Let's take a look at one that is logarithmic. Okay, logarithmic is kind of the opposite of exponential to some degree. In this case, we are increasing or we're decreasing, but more and more slowly as time goes on. Okay, let's take a look at the weight of a child, let's just say from birth to 18 approximately. This isn't perfect, but it gives you some sense of how this works. We'll model this with a logarithmic function. Of course, as you're born, you weigh around 7 pounds. As time goes on, you begin to gain weight quickly. Okay, a 1-year-old, a 2-year-old, a 3-year-old, you're getting heavier faster. But as you get to your adult height and weight, it begins to slow down, and so it begins to, obviously past 18 it may stop, but we're using up to 18 where your weight will begin to you'll gain weight more and more slowly as you get taller as the time goes on. Again, it's not a perfect example, but it's not too bad. Okay, so here we have time, and here we have weight. And again, starting from birth, you don't weigh much, and as you get into 1, 2, 3 years, your weight is increasing rather quickly. But then your weight begins to tail off up till 18, and you kind of hit your adult weight. So you begin to gain weight more and more slowly over the years. Certainly, in your first years, let's say your first 2, 3, 4 years, your weight goes up rather quickly. An infant, to a 3-year-old, that weight really jumps up. And then it begins to slow down. So here is logarithmic growth, which starts out quickly in this case, and then it slows down, okay? It could also be the opposite, where it drops and then slows down, but we usually see it in this format here. The last one is exponential, and I'll do 2 examples for exponential. One example is an quadratic. Misspoke there. One example is an increasing and then decreasing situation. For example, the height of a thrown baseball. Okay, you throw a baseball, it goes up, it hits a peak, and then it comes back down, obviously either to the ground or to the other person's glove you're playing catch with. And this can be modeled by a quadratic function. So let's take a look here. Okay, we'll do time again on the x-axis, and we'll do height on the y-axis. And here's that one. As you throw the ball, it initially goes up, it hits the peak, and then it comes back down. Okay, so there's kind of the height of a baseball, a football. This is also used for, if you think about the old cannons back in Revolutionary War or Civil War days, where the cannon was fired up in the air, it makes a parabola and then comes back down. So here is an increasing and then decreasing data set, okay, modeled best by a quadratic function, which can be increasing and then decreasing here, okay? However, you could also have the opposite situation where you are decreasing and then increasing. That's also a quadratic. And my example here is the value of a classic car. Cars, of course, start off being expensive, and then their value decreases. But if it's a classic car, the value will hit a bottom, and then it'll begin to increase as people seek it out. Perhaps it's a rare car. Perhaps Yeah, perhaps there weren't that many made, and then they're just as they begin to begin to be destroyed, or they begin to go to ruin. The people who took good care of them, the value begins to increase. This is also a quadratic modeling. So we'll go and we'll create a very simple XY axis again in the first quadrant. And again, we're looking at this over time, and here's the value. And again, with a classic car, the value will start off high. Cars are expensive. And then the value will decrease, and then it'll hit a bottom. And then the value will begin to increase as people begin maybe take an interest in it. It's a 1955 Ford, for example, that gets popular for some reason, maybe because of a special rear design, tail fin or something, or something that's part of what made it unique. So here's kind of another example of a quadratic function in which you have a decrease and then an increase. Okay, so all we're going to be looking at here is we're going to look at a scatter plot and see which one of these it looks most like. Okay, so we'll do a few examples here. We're going to use Desmos, which I need to make sure is turned on. There we go. Okay, let's take a look at some examples. Alrighty, whoops. Okay, create a scatter plot for the data in each table using Desmos. Use the scatter plot to determine if the data are best modeled by a linear function, an exponential function, a logarithmic function, or a quadratic function. Here's the first example. In this case, you can see the x values are increasing, and the y values, well, they're also increasing. They tend to be increasing. Well, we got a jump of 0.7, a jump of 0.2, and then 0.1, 0.1. Well, let's see how that's being modeled. Okay, what does that look like in Desmos? Okay, not sure about that. I had to do a quick change of something there. Okay, let's see here. I got it up for you. Okay, so we're going to go into Desmos. We're going to go to the plus symbol. We're going to add a table. Okay, we're going to put our data in, and Desmos will plot it for us. Give me a second to move some things. Okay, so we had our first point was 0, and the y was 0.3. So there we have it up here. Tap for our second point was 8, and then 1. And you can see Desmos has already started plotting on their -10 to 10 graph. And then we went to 15, and 15's y value was 1.2. And then we went to 18, and 18's y value was 1.3. And our last point was the point 24 with a y value of 1.4. Okay, so we put our data in, and we can press this plus sign, right, this little plus magnifying glass, and that will make our graph conform to our data. And so there's our data. There's our graph. The data looks like on the graph, it likes to go from 0 to 2 in the y direction, and from 0 to 30 in the x direction, so Desmos gave us. And you can see what's going on here. We started here. We got a nice little jump here. And then we jumped a fair piece, we jumped some more, but not quite as much. And then we jumped some more, but not quite as much. And then we jumped some more, but not quite as much. So this has a rapidly increasing start, and then it begins to increase slower and slower and slower. And that would be an example of a logarithmic function that would best model this data. Okay, so we want to kind of put a log function in here that says this looks like it's logarithmic. Quick start, and then it continues to increase, but it increases a little more slowly each time. So we'll go to here, and we'll simply note, and I'm not going to worry about drawing this graph, we'll just simply note that this appears to be best modeled by logarithmic function. Okay, let's look at the second example here. Notice their x values are kind of random. They're not in an order from least to greatest or greatest to least. That's okay. We can put them in just like this, and Desmos will show us what it looks like. Okay, so let's take this out, and let's go back into Desmos. Okay, and I'm going to go ahead and press the, I'm going to clear this and press the X, go back and press the plus to get my table, another table in here. Okay, so my points here, my first point was the point 0, 4. The second point in my table was 2, 0. Okay, looks like, yep, so we're kind of on there. Let's see, the next point here was 3, 1. The next point in here was 1, 1. And the final point in here is 4, 4. Okay, so now let's plus this plus. Remember, Desmos adjusted the graph to the previous set of data. So I'll press this little magnifying with the plus here, and I'll take a look at this, and here are my data points. And we can see here, this is coming as we go from left to right. Starting up here, we're coming down, we're hitting a bottom, and we're going back up. Well, that is a quadratic. This data can be best modeled by a quadratic function that opens up. Think about that classic car example. You pay a fair amount for the car, its value decreases, it hits a bottom, and then because it's a classic car and people start to want it, its value then begins to increase, as an example. So it looks like this data over here can best be modeled by a quadratic function. Okay, we'll go back to here and we'll simply note that this set of data, whoops, I want to spell the word quadratic first, can best be modeled by a quadratic function. Okay, let's look at a last example here. Again, we'll note that my x values are not in any order. That's okay. It's nice sometimes to have them go from least to greatest or greatest to least, because we maybe can tell what's going on. But in these two examples, the points were just put in, it appears randomly, but that's okay. We can still plot them, and then we can look at the graph and see what's going on. Okay, so let's go back to here. Okay, line up my Desmos screen again for you, and I'm going to go ahead and close this one out. I'll press the plus and create a new table, and my 5 points are 3, 11. Second point is 0, 4. Third point is 2, 7. The fourth point is 4, 19. And the fifth point is 1, 5. Let's take a look at what this one's doing. Again, we'll notice that this graph was aligned to the previous table of values. So we're going to press this little magnifying glass with the plus. Well, there we go. Well, this one looks okay. So here we started here, and we're starting to, we increased a little bit, increased a bit more, increased more, increased more. So this is having that increasing faster and faster and faster look. It's having that exponential look to it. Again, it's always increasing, but it starts off increasing slowly. It went up only 1, then it went up 2, and then it went up like 4, and then it went up like maybe 10, or no, maybe not quite 10, maybe 8. So it's increasing faster and faster and faster. That is the mark of an exponential function. So we'll go back to here, and we'll note that this one appears to be exponential. So to summarize, generally what makes the most sense is to take the points you're given, put them on a graph, and then take a look at what the graph is suggesting and make the decision, is this a linear function? Is this an exponential function? Is this a logarithmic function? Or is this a quadratic function?